In this video, I'm going to introduce spherical coordinates. We've seen that cylindrical coordinates can give us simpler integrals to work with, but there will still be some regions in R3 that will be complicated even with cylindrical coordinates. But we can also represent a point in R3 using spherical coordinates as P of rho, phi, theta. These coordinates specify a location by the distance from the origin, which we call rho, the angle phi that is between the positive z-axis and the line between the origin and our point, OP, and the angle theta that measures the rotation about the z-axis from the positive x-axis in a counterclockwise direction. The intervals for our spherical coordinates are given by 0 is less than or equal to rho, which is less than or equal to theta, 0 is less than or equal to phi, which is less than or equal to pi, and 0 is less than or equal to theta, which is less than or equal to 2 pi. It's important to understand that there are contexts that will reverse this angle notation, especially in physics, where they will swap the meaning of theta and phi. The key is to know that the middle coordinate in spherical coordinates will always give you the angle between the positive z-axis and the line from the origin to the point, while the third coordinate will be the angle of rotation around the z-axis measured counterclockwise from the positive x-axis. So it really doesn't matter what we call them as long as we pay attention to where they occur in the ordered triple, but be careful to not let it confuse you. So I want to talk about the transformations between rectangular and spherical coordinates. When I go from rectangular to spherical coordinates, I have rho squared is equal to x squared plus y squared plus z squared, and I use trigonometry relationships to discover what phi and theta are. I may have to actually draw a cross-section of my volume in order to set up right triangles and use the trig relationships to do so. If I want to go from spherical to rectangular coordinates, x is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta, and z is equal to rho cosine phi. Examples of sets of points in spherical coordinates will include things like a cylinder. In spherical components, it's a set of all points rho phi theta such that rho is equal to a times the cosecant of phi, and 0 is less than or equal to phi, which is less than or equal to pi. We could also express a cone using spherical coordinates. The cone is a set of all points rho phi theta, where phi is equal to phi naught, and phi naught is not equal to 0, pi halves, or pi. I can also represent a sphere of radius a centered at the origin in spherical coordinates. The sphere will be the set of all points rho phi theta such that rho is equal to a and a is greater than 0. In other words, rho will be a constant distance from the center to the surface of the sphere. I could also represent a sphere of radius a greater than 0 with a center at the point 0, 0, a. This will be the set of all points rho phi theta such that rho is equal to 2a times cosine phi, and 0 is less than or equal to phi, which is less than or equal to pi halves. I can also represent a horizontal plane in spherical coordinates. My horizontal plane will be given by the set of all points rho phi theta such that rho is equal to a times the secant of phi, and 0 is less than or equal to phi, which is less than or equal to pi halves. And I can represent a vertical half plane in spherical coordinates. The vertical half plane looks just like it does in cylindrical coordinates. It is a set of all rho phi theta such that theta is equal to theta naught. So let's work an example real quickly. We want to identify and sketch the points in spherical coordinates that are given by the set of all points rho phi theta such that rho is equal to 2 times the cosecant of phi, and 0 is less than or equal to phi, which is less than or equal to pi. Since we're given rho is equal to 2 cosecant phi, we know that rho times sine of phi is equal to 2. We also know that x squared plus y squared is equal to rho squared sine squared phi cosine squared theta plus rho squared sine squared phi times sine squared theta. Using rho sine phi is equal to 2, I get 4 cosine squared theta plus 4 sine squared theta, which is equal to 4. This gives me x squared plus y squared is equal to 4. And it tells me that all points on the surface satisfy x squared plus y squared is equal to 4, so that my surface is a cylinder of radius 2 centered on the z-axis. And I can represent it simply by any cylinder centered on the z-axis of any height that we might need. In order to formally define triple integrals in spherical coordinates, I will let f be continuous over the region defined by d is equal to the set of all points rho phi theta, such that g of phi and theta is less than or equal to rho, which is less than or equal to h of phi and theta. A is less than or equal to phi, which is less than or equal to b, and alpha is less than or equal to theta, which is less than or equal to beta. Then f is integrable over d, and the triple integral of f over d in spherical coordinates is given by the triple integral over d of f of rho phi theta dv is equal to the integral from alpha to beta of the integral from a to b of the integral from g of phi theta to h of phi theta, f of rho phi theta, rho squared sine phi d rho d phi d theta. Now again, just like before, this triple integral represents a volume on the region D if f is equal to 1. And if f describes a density of an object, then the triple integral gives me the mass of that object. Let's work an example. I want to evaluate the given integral in spherical coordinates. I'm given the triple integral over d of e to the negative x squared plus y squared plus z squared raised to the 3/2 power dv, where my d is the unit ball. I know that in spherical coordinates, I'm looking for the integral from alpha to beta of the integral from a to b of the integral from g of phi theta to h of phi theta of f of rho phi theta rho squared sine phi d rho d phi d theta. Since we're given a unit ball for my region, we know that rho will go from 0 to 1, that theta will go from 0 to 2 pi, and that the limits on phi will go from 0 to pi. I can construct a unit ball so that I can see my uniform distance from the center out to the sphere will be 1 in all directions. Now I need to look at my integrand. E to the negative x squared plus y squared plus z squared raised to the 3/2 power is the same thing as e to the negative rho cubed, so that my triple integral now becomes the integral from 0 to 2 pi of the integral from 0 to pi of the integral from 0 to 1 of e to the negative rho cubed times rho squared sine phi d rho d phi d theta. Now I'm going to perform the integration by working from the inside out. I take the integral from 0 to 1 of e to the negative rho cubed times rho squared times sine phi d rho. I get negative sine of phi times the quantity e to the negative 1 minus 1 over 3. This is the integrand for my middle integral. And I now take the integral from 0 to pi of negative sine phi times the quantity e to the negative 1 minus 1 over 3 d phi. This becomes e to the negative 1 minus 1 over 3 times cosine of phi evaluated from 0 to pi. This gives me e to the negative 1 minus 1 over 3 times negative 1 minus 1, or negative 2 times e to the negative 1 minus 1 divided by 3. Now I evaluate the outermost integral, the integral from 0 to 2 pi of negative 2 times e to the negative 1 minus 1 over 3 d theta. This is equal to negative 2 times e to the negative 1 minus 1 over 3 times theta evaluated from 0 to 2 pi. I plug in that limit of integration and simplify, and I get negative 4/3 pi times e to the negative 1 minus 1. I want to work another example. Here I want to find the volume of the cardioid of revolution on the region D is equal to all points rho phi theta such that 0 is less than or equal to rho, which is less than or equal to 1 plus cosine phi, 0 is less than or equal to phi, which is less than or equal to pi, and 0 is less than or equal to theta, which is less than or equal to 2 pi. I set up my triple integral with the limits of integration I was given. I get the integral from 0 to 2 pi of the integral from 0 to pi of the integral from 0 to 1 plus cosine phi of 1 times rho squared sine phi d rho d phi d theta. The innermost integral is the integral from 0 to 1 plus cosine phi of rho squared sine phi d rho. This is equal to sine phi rho cubed over 3 evaluated from 0 to 1 plus cosine phi. This gives me sine phi times the quantity 1 plus cosine phi cubed divided by 3. I'm going to plug this into my middle integral and factor 1/3 out front. I get 1/3 times the integral from 0 to pi of sine phi times the quantity 1 plus cosine phi cubed d phi. I'm going to use a substitution in this integration, and I get negative the quantity 1 plus cosine phi raised to the 4th power divided by 12 evaluated between 0 and pi. I get 4/3. Now I take my last integral, the integral from 0 to 2 pi of 4/3 d theta, which is equal to 8/3 pi. Now you get to try it. Pause the video and use spherical coordinates to find the volume of the region inside the cone, described by z is equal to the quantity x squared plus y squared to the 1/2 power, that lies between the planes of z equal 1 and z equal 2. When you're ready, restart the video to check your understanding. The first thing I need to do is convert my integrand into spherical coordinates and then determine the proper limits of integration. I know that 1 is equal to the quantity x squared plus y squared raised to the 1/2 power at the z equal 1 plane, which gives me a circle of radius 1. And I know that 2 is equal to the quantity x squared plus y squared raised to the 1/2 power at the z equal 2 plane, which gives me a circle of radius 2. If I look at the points on the cone that intersect the two planes and that lie directly above the x-axis, these points will have coordinates 1,0,1 and 2,0,2 respectively. Using this and similar triangles, I find out that phi is equal to pi over 4 at the surface of the cone, so that phi is going to go from 0 to pi over 4. Now if I use x is equal to rho sine phi cosine theta and y is equal to rho sine phi sine theta, I get z is equal to rho cosine phi. At z is equal to 1, this tells me that rho cosine phi will give me rho is equal to secant phi. And at z is equal to 2, rho cosine phi gives me rho is equal to 2 secant phi, so that my limits of integration for rho go from secant phi to 2 secant phi. A full cone will require theta to go from 0 to 2 pi. This gives me all my limits of integration and my spherical components. I get the integral from 0 to 2 pi of the integral from 0 to pi over 4 of the integral from secant phi to 2 secant phi of 1 times rho squared sine phi d rho d phi d theta. I'm going to evaluate this integral by working from the inside out. The integral from secant phi to 2 secant phi of 1 rho squared sine phi d rho gives me rho cubed sine phi over 3. I plug in my limits of integration from secant phi to 2 secant phi and simplify, and I get 7/3 secant cubed phi times sine of phi. This becomes the integrand in my middle integral, the integral from 0 to pi over 4 of 7/3 secant cubed phi sine phi d phi. This is equal to 7/6 times cosine phi to the negative 2 power evaluated from 0 to pi over 4. This gives me 7/6. This becomes the integrand in my outer integral, and I take the integral from 0 to 2 pi of 7/6 d theta, which gives me 7/6 theta evaluated from 0 to 2 pi, which gives me 7 pi over 3. I can do a very simple check using the formula that I already know from geometry for the volume of a cone. The volume of a cone is given by 1/3 times the area of the base times the height, in this case 1/3 pi r squared times h. If I compute the volume of the cone with a base at z equal 2 and subtract from that the volume of the cone with a base at z is equal to 1, I should get the volume between the two planes. This gives me 1/3 pi times 2 squared times 2 minus 1/3 pi times 1 squared times 1, which is equal to 8/3 pi minus 1/3 pi, or 7/3 pi. This is exactly what I got with my triple integrals. This is how I can use spherical coordinates to compute volume or mass using triple integrals. Be sure and let me know if you have any questions.